Hey everyone, this is Mrs. Martin here today with your notes, or kind of just a review on the introduction to trig functions. So to start out today, we're going to review what most of you have already submitted. Thank you for doing so already. If you haven't, please go ahead and do that so we can continue on. It's fine if it's late. I know a lot of us have been doing AP exams, so I'm glad you've been able to take some time and focus on that. I know that was a lot of stress, and hopefully you're feeling confident about your work. And now that that's over, we can finish up our last couple of weeks of pre-calculus. So again, to start this video, we're going to review the introduction part 1. And then about halfway through the video, I'm going to give you a few pointers on how to complete part 2 of this assignment, which involves some Ferris wheels. All right, so let's get started. I've written here in Desmos the 4 functions besides the parent function that you were supposed to work on in the table for your representing trig functions. So again, it's here. Okay, mine is a little longer because it has both parts 1 and part 2, but for you guys, you only have these 3 pages down here at the bottom where you had to fill in the boxes and determine what those values were to see what was happening in this graph of cosine. Okay, quick note, the x values used here are in degrees. So some of us, when we submitted our assignments, we were getting some weird pictures, and odds are it's because our calculator was set to radians. Now, normally I would use radians because I think it helps us keep patterns a little bit easier. The numbers feel a little smaller. However, Sheets doesn't really have, or at least in a good representation way, it didn't have the use of pi. And without the use of pi to look at in Google Sheets, I went ahead and went with degrees. I'm sure there's some things that I could probably tweak here so that pi comes up. But for now, and to make our lives easier, we went ahead and worked in degrees. Okay, so if you're getting funky numbers and your pictures are not really looking cosine-ish, the possibility is your calculator is set to radians, and you can change that, set it to degrees, and then push forward. Okay, so just to have some conversation and not take the time to fill out that table, that's your job, right, to fill out this table, I'm just going to use Desmos to discuss a few things. Okay, so again, I've set my x-axis to degrees. If you're using Desmos, in the settings, you do have to make sure that degrees is selected and not radians, or else again, if I've got radians up here, I'm going to get a really hard to look at picture, as you can see. So I'm going to stick with degrees. I went from about -5 to 365 just to give myself a little extra space on the ends there. And I went steps of 45. That's pi over 2. I went 45 just so I can get a good picture of this. And my y-axis, I went -4 to 4. All right, so here's my parent function. And there are a few things that you probably talked about in Algebra 2, but we want to make sure that we're still aware of those things here. So first off, we've got a height here. And actually, let me draw that right where it goes. So right where I've got a max, and down here to this sort of midpoint, right? Because I have essentially, I've got a midpoint here where I cross through my sine function. In this case, we've got it right through on the x-axis. The height up to the maximum, and as a matter of fact, down to the minimum as well, we call those, and you might remember the vocabulary, we call that an amplitude. Okay? Same thing, okay? Amplitude is the pink here, where at every max and min, I've got this given height going. Okay, let's see how that changes when I look at 2 cosine. So let's change over here to 2 cosine. We're going to add that in. And let's kind of look at how that amplitude changes, right? Because the center line didn't change. Even the width of the graph didn't change, right? It still intersects at 90 and 270. So really the only thing that changed is this amplitude. And how much did that change? So when I look at this, and I'll use green to go with this function, my amplitude now is up here at 2, down to my center line, that line that cuts our cosine graph in half. So now our amplitude is 2. So A equals 2. And I see 2 right here in my function. So at this point, it's probably pretty safe to say that amplitude is going to be the coefficient in front of cosine x. Well, let's just make sure. I know this wasn't part of your assignment, but just to confirm here, if I type 3 cosine x, then technically my cosine graph should have an amplitude of 3, and I can see very clearly that it does. It comes all the way up here to 3, still a center line, hasn't gotten wider, it's still intersecting at 90 and 270. So it's very clear here now that we can probably assume amplitudes are written as the coefficient of our trig function. So let's go ahead and write that in for ourselves, just so we keep track of that. So I'm going to use pink for amplitude. Amplitude times our parent function, which is cosine x. Okay, so let's keep that one in mind as we continue to work through these. I'll erase this stuff here so it doesn't get too crowded. And let's keep moving. So now I'm going to go ahead and let's go ahead and get rid of 3 cosine x because that wasn't part of our assignment. We just wanted to make sure that our conclusions made sense, that the amplitude was in fact the coefficient in front of cosine x. Now we've got some other things happening here. So just to get rid of 2 cosine x, let's look at 1 plus cosine x. Now we talked about that line that cuts cosine in half horizontally, right? So let's use blue for that. In the original parent function, we saw very clearly that it cuts it in half on the x-axis. The x-axis is that line that cuts cosine in half. Many of you know what's going on when I have a 1 plus cosine. I'm sure many realize that that's just our vertical translation. So when I'm looking at 1 plus cosine, I notice that all my points went up 1 unit, right? So here I am taking all these important points and they're traveling up 1 unit. Okay, notice I picked these points because they're maximums, minimums, and x-intercepts, okay? And so if everything's moving up, it's safe to confirm that this is still a vertical translation. Okay, that's still happening like before with our parent functions and our transformations of functions in the last unit. Okay, so with that in mind, we're going to go ahead and call that k, just like before. Where I take my function and I shift it up. And one thing that's really important to note here is that the line that cuts this cosine graph in half is now at the number 1. Okay, so that line travels as well. We can't call this an asymptote. I know some people are tempted to call that an asymptote because it's a sort of line that we're following. But since cosine never approaches that line and it just kind of oscillates up and down on top and the bottom of that line, we're not going to call it an asymptote. But we do know that that figurative line exists. And we know now that because it was plus 1, the whole line shifted up 1. So just keep those in mind when we go into the Ferris wheel activity. Now that we've looked at that, let's go ahead and erase the extra stuff here. There's one more function that's doing some interesting stuff. And that is this function here, cosine 2x. Now this one's a little new. We didn't work too much with coefficients inside of the parentheses with x, especially when we were working with other functions in the prior unit. But working with cosine, we can kind of see something weird going on here. Okay, first of all, some of you called it more wiggles. There are more little wiggles or more bumps in the cosine graph when I had cosine 2x. And let's think about what this means. First off, nothing's changed with the line that cuts the cosine in half, right? That's still there. It's still cutting the graph in half. So that's good. Our amplitude has not changed. It's still 1. So it becomes obvious that this 2 inside with x is somehow changing how many bumps appear in our graph. We call this one the horizontal stretch. And generally in your functions, we'll use a letter B in there. Okay, and so one way to determine what B is when we're looking at cosines is to try and determine how many cosines are in a 360. Okay, so let me try and word that a little bit differently because that might be weird to think about. So I've got 360 degrees, right? Or 2 pi. 2 pi, that means the same thing. And that's an entire rotation of a circle. Now in the parent graph for a rotation of a circle, and then let's think of the unit circle. I know how much you guys love the unit circle. For cosine x, that means we started here and we went around the unit circle 1 time. All right, so we're starting here at 1 for cosine, and you know, just to clear up why we start at 1 for cosine, if I've got the unit circle, here's the center. If I'm at 0 degrees, let's really quick refresh our memory what's cosine, right? So you guys remember SOHCAHTOA. So cosine is equal to adjacent over hypotenuse. Well, in the unit circle, our hypotenuse is equal to 1. And so if it's equal to 1, then I can just get rid of it in the denominator. Why even have that, right? So ultimately, in the unit circle, because the hypotenuse is 1, right? That's by definition, unit circle has a radius 1. I can just look at cosine as the value of the adjacent side, right? Here's theta. So our adjacent side. And if I'm going from the center out to 0 degrees, my adjacent side is 1, right? It just matches up with the radius. So that's why our cosine functions are starting at 1. Now, by the time we get to 90, let me erase that just for a second. By the time we get to 90, so here I am traveling around the unit circle, I get to 90. Here I am, 90 degrees. And notice that since my triangle doesn't have a base now, it's just kind of so skinny that it's a line pointing up, that's why I'm ending up at 0. There is no adjacent side anymore. Okay, just trying to understand how this unit circle thing's working. Okay, so let's get rid of all of this and keep moving. So here I am traveling along the unit circle. I get to 180 degrees. So now I've gone 0, 90, 180. Continuing back up to 270. And finishing off up here at 360 again, okay? Which is just right where we left off, or we began at 0 degrees. Okay, so one period, we use the word period in trig, one cycle of our cosine function looks like this wave where I start at 1, I travel down to -1, and then end up where I started at 1. Now, what does this have to do with cosine 2x, right? So let's look at that. When I look at cosine 2x, I start at 1, still traveling down to -1, traveling back up to 1, and notice I'm only halfway through the 360 degrees. Okay, so I've already gone through this hypothetical cycle of cosine. But of course, my goal is to get to 360, so if I continue again, notice I get an entire other cosine function. So if I'm thinking of it in this way, to get how many cosine functions, this shape where I go from 1 to -1 to 1, how many do I have in the course of 0 to 360? You guys might be seeing that we have two. We've got two cosine graphs squished together in what would normally be one parent cosine graph. And that's where I'm getting this 2 from. Let's confirm our suspicions by trying out maybe a cosine 3x. So let's see what happens when we have a cosine 3x. So down here, I'm going to type into Desmos cosine 3x. All right, and again, we're going to go through this and just check how many cosines do I have. So I've got 1 here, a second one, and a third one. Okay, so with this in mind, we know that cosine bx is really how many cycles of cosine do I pass through getting from 0 to 360 degrees, or 2 pi. Okay, so let's keep these things in mind as we move in to part 2 of this video, which is the Ferris wheel activity. All right, so here we are on our Ferris wheel activity. You have access to this on Schoology, so you could totally just open it up and work on it while we go through this video together. And I've got here over on the right a picture of a Ferris wheel, so we can kind of have a visual of what's going on. Okay, and for the sake of this assignment, we are going to be starting right over here at the bottom. Okay, so here's us. There we are. And we're going to rotate counterclockwise just to kind of keep with the unit circle idea. Okay, because our unit circle is traveling counterclockwise. We'll do the same with our Ferris wheel. And we're starting here at the bottom and not at 0 degrees, mostly because it doesn't make sense for you to enter the ride up here. I mean, how did you even get up there, right? So we're going to start at the bottom of our Ferris wheel and continue around. Okay, so it's going to require you to kind of think of your unit circle a little bit differently, but we're going to do our best. All right, so let's read the scenario together. A Ferris wheel is 60 meters in diameter and rotates once every 4 minutes. The center axle of the Ferris wheel is 40 meters from the ground. All right, so let's diagram this. I always like a good picture when we're working with things like this. So just to erase here, and again, a reminder, we are starting in this box, okay? That's our start. So let's diagram this a bit. First, let's start out with our diameter, okay? So diameter is good information to have, but when we're talking about unit circle, it's a little better to think radius, right? Radii are the way to go. So if my Ferris wheel is 60 meters in diameter, then we can go ahead and think of our radius. Now just move it over here to the right so we can see it. Note that every little box in our Ferris wheel is going to be the same, right? By definition, our radius is the same all the way around a circle. Our radius now is going to be 30 meters. Okay, so just from the information we've gathered, Ferris wheel is 60 meters in diameter. So we've got a radius of 30. That's half of 60. The other information that they give us is that when we're traveling around this Ferris wheel here, I start here at 0 minutes, right? I get on the ride. And then as I go around this Ferris wheel, here I go, top, side, bottom. When I get here to the end, it's taken me 4 minutes to go around. Okay, that's fast or slow, that's up to you. I personally don't like Ferris wheels, but a lot of people do. 0 minutes, 4 minutes, It feels pretty fast to me. But anyway, so we've gone around in 4 minutes. Okay, again, we're just diagramming the information that we've received from our problem here. The other information that we got is that the axle that's pretty much the piece holding the Ferris wheel up. The axle here is 45 meters off of the ground. 45? 40, sorry. 40 meters off the ground. So this center axle where the Ferris wheel is being held up, this is 45 meters off the ground. Okay? So now that we've got all this information, let's make a few notes for ourselves. First of all, when I get on the ride, how high off of the ground am I? Now your chart, I started it out for you at 0 minutes. It says 10 meters. Oh, I wrote 45 anyway, sorry. 40 meters. So how am I getting 10 meters off of the ground? Nowhere on my diagram does it even say 10 meters. And yet 10 meters is given to me in the table over here on the left. Well, if we think about this, let's think back to the radius of 30, right? So here is my radius 30, okay? But I knew that the whole Ferris wheel, its center itself, is raised off of the ground 40, and so that's how we're getting 10, okay? We're making this conclusion that right here, this height off the ground, obviously I can't get on the Ferris wheel and be starting on the ground. The little box or cubby is usually a little off. We're 10 meters above, okay? And really I just found that by visualizing the 40 meters and then subtracting the radius 30 meters to find the leftover distance. Okay, so now I know when I get on the Ferris wheel, I'm 10 meters off of the ground. You know, you have to walk up those little steps and then hop in the little box. And then I'm traveling around the Ferris wheel and I get back to where I started in 4 minutes. Let's make a few more notes on time here. If I made the whole journey in 4 minutes, how long did it take for me to get to the top? That's about halfway through my journey on the Ferris wheel. I'm sure most of you are thinking half of the 4 minutes, which is 2 minutes. With that same reasoning, how long would it take for me to get a quarter of the way around, or half of the half? And I'm sure, again, many of you are thinking 1 minute. So now I'm going 0 minutes, 1 minute, 2 minutes. And then when I get over here, I'll have traveled for 3 minutes, kind of keeping with this pattern. And finally, on the last one, I'll have traveled 4 minutes, getting back to where I started. Okay. So let's start filling out our table. I mean, we've got all this information now and our diagram's looking pretty full. Let's start entering things into my spreadsheet over here on the left. So we've already got that when we start, we're at 10 meters off the ground. We also know that once we hit 4 minutes, because remember our cycle around the Ferris wheel is 4 minutes, once I get to 4 minutes, I'm going to be 10 meters off the ground again. And what if there's nobody in line, so the guy running the Ferris wheel says, hey, want to go again? And we say, sure. Then the next time I'll come back to the beginning will be in 8 minutes. Okay, so we just have these 4-minute cycles going. So now we've got to work on filling out the rest of these. That way, hopefully we can get a nice graph over here on the right. So how high off of the ground are we when we are at 1 minute? So just to remind ourselves, that's over here 1 minute and we are this far off of the ground. So how far off the ground is that? Well, lucky for us, our diagram is pretty detailed, and we can see that the 1 minute mark is lined up with the center axle, the part that's being held up, that the Ferris wheel is being held up by. And if we're at that same height, we know that the center of our Ferris wheel is 40 meters off the ground. And so if I'm lined up with that line there, that means we are 40 meters off of the ground. How about 2 minutes? Now, it's really tempting to say 60. Sometimes I want to say 60. And why would we say 60? Well, I would say 60 because the diameter of my Ferris wheel is 60. Right? So to get to the top, that's 60 meters. But let us not forget our little 10 meters off the ground where I start. Okay? So really, if you think about it, it's the 40 meters plus a radius of 30 meters. Okay? However you're looking at it, diameter plus 10, radius plus the height of the center of the Ferris wheel off the ground. Again, whether you're looking at it the first way or the latter way, we are now 70 meters off of the ground. By the time we get back to 3 minutes, hopefully you guys are catching on this pattern now. Again, we're lined up with the center of the Ferris wheel, so we are 40 meters off the ground. And this is just going to keep happening over and over and over again. All right, that's the characteristic of our cosine graph. You're just traveling over and over and over again in the same pattern. Okay, so there's my graph. Spreadsheets isn't the greatest at making cosine graphs, but there it is, the basics. It's enough for us to get some information because the next part of your assignment on this page is to write an equation to model this situation. Okay, so let's go back over here and make a few notes for ourselves. First of all, let's scoot this over. We're done with that diagram for now. We have a format that we should be following, right? And that format looks like this. Let's stay color coordinated here. I think we used pink, so our amplitude times our parent function. Okay, we added some sort of vertical translation. And then, I think this was purple in our last one. We had some b value often that either squished or stretched out our cosine function. Okay, so let's go back over here and let's look at some of these points. Okay, and it's kind of hard to see in this graph, but we're going to do our best. First off, if we remember in the first part of this video, we had, oh, and let me annotate here. We had 0 as our halfway point, our midpoint through our cosine graph. Right? Well, it's not there anymore, obviously. The whole graph is above that line. Where is the center now? Where is that halfway point? Hopefully you guys are seeing that the halfway point is now at 40. There, I just cut my cosine graph in half. Now, where are we hearing 40 from? Where was 40 in our word problem here? It was at our center point for our Ferris wheel, right? Let's scoot this over. There it is. Center point for Ferris wheel was 40. And it just so happens that the center line for our cosine graph is 40 as well. Isn't that nice? Coincidence, right? So thinking of it that way, our center line just traveled up 40 units, meters in this case, right? And so since I've traveled up 40 units, that means all my points have traveled all together, right? All together, they've moved up 40 units. And so now I've got a K value. Oh, sorry, wrong pen. I don't want that to disappear later. So now we've got this plus 40. Okay, so that's a start. We just moved our whole cosine function up 40. What else is happening here? Now we've got our amplitude, right? It's always nice to go for amplitude. So now that we've got our center line drawn in here, my amplitude goes from the max or the min to the center line. There's my amplitude. And what value is that? Well, our maximum is 70. Our midpoint here, our midline is 40. That means our amplitude is 30. Okay, so now over on our equation, I can go ahead and write in 30 cosine x. Now I'm going to leave myself some room in front of x because I know something's got to be happening with this stretch or shrink. I mean, already we can see, and let's use purple here. Already we can see that I've got a cosine graph here, and it only took me about 4 minutes, right? 4 minutes to cycle through. So we know something's it didn't take 360 like the parent function, so something's happening with that horizontal stretch. Before I continue, I do want to make one little point here. Let's remember what our cosine graph looks like, right? So just to do a quick sketch down here, this is my XY axis. Cosine graphs look like that, right? So they start up here at the top, go to the bottom, and then come back to the top. What happened with this graph? Well, if we look over here, we started at the bottom, then went to the top, back down to the bottom, and so on and so forth. So really what's happening is now our graph looks like this. You guys are great at transformations. What happens to make our graph do a little flipperoo like that? And if you're thinking back to transformations, hopefully you are remembering that to do the old flipperoo, that's a minus sign out here in the front. Okay. Now, the minus sign is a little weird to think about. I mean, how do you do minus a distance, right? Well, if we're looking over here back at our Ferris wheel, maybe you can just think of it as if here's my center line, then I'm starting at negative 30. Okay, so that might help us be able to grasp the minus 30 a little bit. It also might be helpful for those of us who are really good at transformations, and just remember that if I'm flipping my cosine over, that is a negative A, okay, negative amplitude. All right, so I know this is a lot. You guys are doing great so far. We've got that one more purple number left to fill in. So let's think about this. We said that the purple number is pretty much how many times I cycle through cosine within the course of 360 degrees. So here's 0. And how many times until we get to 360? And I'm going to figure this out, I'm going to start by asking you this. How long did it take to cycle through one period of cosine? Many of you are probably thinking 4 minutes, right? Starting at the bottom, we went all the way around, it took us 4 minutes to get back to where we started, okay? So this 4 minutes, I mean, think about what that looks like. That's 1, 2, 3, 4, and that's probably not even small enough. And I did one of these, okay, 4 minutes. So if each one takes 4 minutes, and I have 360 blah, 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 all the way over here, how many times does 4 minutes fit into 360? Hopefully your brain's thinking division. How many times does 4 fit into 360? 90. All right, now does 90 make sense? Now all of a sudden I'm just gonna come over here and type in 90. I mean, that looks like a pretty large number for our horizontal stretch? Well, if I look back at my Ferris wheel over here, in essence, it does make sense, okay? As I start at 0, how many times till I get to that 1 minute checkpoint? How many degrees? That's 90 degrees. Okay, and then I continue to my next checkpoint, that's another 90 degrees. So you can kind of think of it like that as well. Just this idea of traveling through to get to the end. Okay, so there's my function. To confirm, okay, because sometimes these things, we make up these equations and then we're ready to move on, but we haven't even confirmed that this is in fact true. Like, does this equation really work for the function we just created? We're going to check, okay? Checking is important. So let's scoot back over here so we have a table to reference. Let me clear all these drawings. And let's plug in some numbers, okay? And a lot of these numbers you still have from the previous part 1 assignment where you had the parent function cosine, okay? So just to run through a few of these together and then you can check the rest on your own. Let me find myself some space here. All right, so we've got x values. Okay, and our current function is -30 cosine 90x, and then we've got plus 40. And again, just to recap, this was our radius of our Ferris wheel, right? The negative just gave us the direction. 40 was the height of, sorry about that, height of the axle, okay? And the 90 is the one that's kind of strange to think about. Sorry, I've lost my pens. The 90 comes from the fact that each cycle takes 4 minutes and we're going to have the 90 cycles. So number of cycles, I should not be writing that there. We're going to put math there in a minute. So 90 is the number of cycles, or I should use the word periods, in 360 degrees. Okay, now just to be clear, this might change, or this will change, if I'm thinking instead of 360 degrees, I'm thinking radians. And actually in your matching activity at the end of this lesson, it does transfer into radians. So just be aware that you might be using radians. You know how to switch to those. You just did the unit circle. Even if it takes you a couple minutes longer, that's totally fine. So let's do some of these. We're just going to go ahead and go through 0, 1, and 2. And then again, you guys can double check the rest. But really, once I check a few, we start to get an idea of a pattern, right? Because cosine and sine, those guys are all just patterns. So let's plug some stuff in. I've got -30 cosine 90 times 0 plus 40. So I'll show a little work first here and then I'll erase that out. So I've got here, this simplifies to cosine of 0. And remembering back to our parent function, we can look at that just for a second. That's over here at our intro. Cosine of 0 degrees is 1. So over here, that's equal to 1. I've got -30 in front of that stuff. -30 times 1 is -30, and -30 plus 40 is 10. Okay, and is that what we got on our Ferris wheel? Let's go back here. And it is. We're good to go. 10 is what we saw in the table. All right, so far, the equation that we created is working. Hopefully it keeps working. Let's try with 1. So here's the first one. -30 cosine 90 times 1 plus 40. Now I've got negative 30 cosine 90, because 90 times 1 is just 90. Negative 30, again, I'm going back to my parent function and thinking about cosine of 90 degrees. That's 0. I'm using parentheses to remind myself to multiply. Negative 30 times 0 is 0. And 0 plus 40 is 40. So that's my final answer. And then again, looking over to the left on our table on Google Sheets, we see that when we made our picture and we were thinking about it just in terms of real life and what we know was happening, our height was 40. So that means, again, our equation came through. We're doing a good job so far. All right, so far so good. Let's just test the last one, and I think if our last one works out, if it checks out for us, I'll feel safe enough to use that equation. Okay, so again, I've got negative 30 cosine 90 times 2 plus 40. Okay, and again, I'm going to take it step by step and simplify. These are all degrees, by the way. It's just hard to draw them on here. Cosine of 180 degrees, again, thinking back to my unit circle. Cosine of 180 is negative 1. Negative 30 times negative 1 makes that 30 positive. And 30 plus 40 is 70. So again, looking over at our Google Sheets, at 2 minutes we were at 70 meters. Our equation's looking good, guys. I think we're safe to move on. All right, so before I finish here with this problem, just to confirm, if we're switching over to radians, okay, so what about radians, right? Because usually radians are the ones that we focus on anyway when we're working with trig. I'm just going to use my unit circle. Okay, so instead of using 90 degrees, and I think they said pi over 2 earlier, and I should not have, or for 45. That's just pi over 2 x. Okay, so moving on to Ferris wheel 2, and I'm not going to do this one with you because I want you to take some time to think about it on your own. I just want to set us up with a good diagram so that you can feel a little more confident trying this out. Now, if you want to be daring and try it out on your own, go ahead and pause this video and try doing the Ferris wheel 2 by yourself first, and then come back and we'll see if our answers match up. Okay, so again, if you want to be gutsy and try Ferris wheel 2 on your own, stop the video now and then come back and check in after you're finished to see if our answers match up. All right, so Ferris wheel 2, here we go. We're starting, trying to make a good diagram. Let's read the scenario. A Ferris wheel is 50 meters in diameter and rotates once every 3 minutes. The center axle of the Ferris wheel is 30 meters from the ground. All right, so let's come up with some information here, some diagramming. First off, we've got information about the center axle. Well, let's start with the diameter. Diameter is 50, which makes me kind of sad because it's not going to cut in half to get an even number, but that's okay. 50 meters, I can think of quarters. Half of 50 is 25. So I'm going to focus on a radius of 25 meters. I'll probably need that. I am also told that I'm starting here for 0 minutes. And when I travel around my Ferris wheel, when I get back to the beginning, it's been 3 minutes. So we're zooming around this Ferris wheel a little faster than the other one. Okay, 3 minutes to get around. Of course, the radius is smaller, so you're not traveling as much, but still. 3 minutes. So, let's keep diagramming before we start making any inferences. We just want to get data right now, get information. So we've got the radius, we've got the every 3 minutes, and the last bit of information that we were given is that the axle here is 30 meters off of the ground. All right, so now that we've got all this information, let's break some things down for ourselves. First off, if I'm 30 meters off the ground at the axle, but the radius of the ride is 25, we can go ahead and assume that, or conclude that the height from the ground is 5 meters. Okay, and that checks out with the table and what's given to us already. Now the thing that's a little tricky this time is that I'm not going to mark the top half. It was really tempting the last one because everything was nice and in quarters, right? 4 minutes. But if I'm marking the top half, what's half of 3 minutes? 1.5 minutes. And I don't have 1.5 in my table. So that might not be a good number to focus on. Although we did like it before because it's easy to determine how high off the ground you are when you're there. You're 55 meters off the ground when you're at the top. I'll write it in just so that I know, right? 55 meters. It's good to know, but not really anything that we can put in our table. So now we've got to think, how can I mark this thing where I have 1 minute, 2 minute, 3 minute? Okay, so if at 0 minutes, I'm here, where am I at 1 minute? Okay, so I'm cutting this thing into thirds now. Not quite on the Ferris wheel cubbies because those aren't every 3. All right, and so then now I've got 1 minute and I've got 2 minutes. And it might be tricky to determine the height of this thing, but I think that you can go ahead with this information and determine the equation of this thing. And if you can determine the equation of this thing, it might help you determine the height. A couple of things that our diagram does help us figure out is that at 1 minute, we definitely have to be a little bit less than 55 minutes. Okay, so keep that in mind. All right, and so I'm gonna go ahead and stop there and let you guys continue working on Ferris wheel 2. Again, it's a little trickier than the first one because we're going by thirds and not many of us really like thirds, 4/3. But do your best, I know you can do it. Work through it carefully, follow along with the material that we worked on together for Ferris wheel 1, and I'm confident you'll be able to figure it out. To finish up this activity, you're gonna click on the matching activity sheet, all right? And there's a link here, a hyperlink. Click here to access Desmos and play the matching game. So I'm gonna go down here to Student Desmos. Okay, and it asks me to enter, the class code's already there, so there you can just click join. However, I do suggest that you sign in with Google so that if you lose any of your work or you have to exit, your Wi-Fi goes out, whatever, you can sign back in and go to where you left off. So I'm gonna go ahead and sign in with Google. Okay, there I am. Now I know my stuff's going to be saved as I work. And try to take this little by little, okay? Don't, oh, I did do it in degrees, wonderful. So little by little, try and match them up. I can click on a card and match it with a description and try and match it with an equation. And you're going to do that with all of those. Okay, so take your time. I know there's a lot of cards. I apologize. It is going to be kind of hard to move them and make sure they fit. But I know you got this. You can make it full screen if you want. Give yourself a little extra room. So try them out. See if you can match the equations with the graphs. And I'm confident you'll get some things figured out on here. One last thing. Some people were submitting their trig functions assignment and they were having a little bit of trouble. When you click file and download as a PDF, It was only giving me the one page. And that's because your export says current sheet. So just change that, click on workbook, and it'll send me the whole thing. After you submit and you get your score, please check out your submission on Schoology. Schoology allows me to put little notes. Click on your assignment when it's in a PDF and leave notes for you so you have specific detailed feedback. That way, if you're missing any points, you can just go into where you saw that feedback, fix it on your document, and resubmit so I can give you those points. Okay, again, our whole goal right now is to become masters at this material. And if it takes you a second, third time, that's no biggie at all. You're learning every step of the way. All right, guys. Well, that's it for me today. I think you did a wonderful, wonderful job. Keep it up. I'm really proud of everything that you're doing and all this effort you're putting in. And I appreciate you guys coming into Zoom so often. The Zoom yesterday really helped me design this video today. So whether you know it or not, you guys help me every single day. So I miss you all. I hope to hear from you soon. And I hope you enjoyed the video. Bye-bye.